All right, gang, here we go. So this is Physics, Unit 4, Part 3. We're talking about Kepler's laws. This will be a pretty short and simple unit or part here. Um, just a couple of things you just need to know about Kepler's laws. Kepler was an astronomist, physicist, mathematician who came up with three laws of planetary motion, and he based his ideas off of the original concepts provided by Copernicus. Remember, Copernicus is the really first guy who said the planets orbit the sun, not the everything else orbiting the Earth, and then also Tycho Brahe. Okay, now so Tycho, Mr. Brahe here, he is best known for getting very, very accurate data about the movement of astronomical objects, specifically planets. So before his time, not very many people, like, there were some recordings for things, but he was on average like 5 times more accurate for his measurements of the movement of planets. So Kepler came along and used his ideas, and Kepler would actually he had notebooks upon notebooks, pages upon pages of him trying to establish the motion of the planets and predict their motions based on mathematical formulas, and so that led him to make his first law here. He came up with three laws of motion. We're just going to talk about each one individually in the next couple of slides. So his first law was based on his idea. Like, he kept looking at these laws or these motion of the planets and trying to develop. They automatically assumed that the planetary motions would be circular. Okay, because circles are pretty imperfect, and so why wouldn't everything else be also pretty imperfect? And so he developed all sorts of equations trying to make the circle fit the data Mr. Brahe had figured out about the motion of the planets. And so he tried dozens and dozens and dozens of different types of circles at different angles and different heights, so on and so forth, to try to get them to fit, and never could quite get them to work out. And then until he could try to make them fit as an ellipse. Okay, so once he did that, then the motion of the planets were pretty much exactly right. So it's an ellipse. And remember, you should remember from geometry class that ellipses have two specific areas in them that are called foci, right? Or focal points. And there's one here and one here. Okay, and ellipses are special. They're not just ovals, but they're special shapes that have a specific relationship between the distance between the foci and then the distance the foci have to the edges of the circle. Okay, so anyway, once they were established that they were elliptical paths, then they were easy to predict. Okay, easier at least. Okay, now it just so happens that part of the reason that it was so tricky to figure out what the orbits were is because they were just looking at the orbits of the planets. All of the planets that orbit the sun, except for Mercury, actually have very nearly circular orbits and not elliptical orbits. So they are elliptical, but they don't really look that way. They kind of look more circular than anything else, except for Mercury is quite elliptical. But anyway, and so that was another reason it was kind of hard to spot. Kepler's second law, he said that equal areas of the ellipse are swept out in equal time periods. So like if your planet goes from here to here in a specific time, we could say that's like 1 hour, 35 days or whatever, and it goes from here to here, and you drew a line to where the sun is. Oh, the other thing is that he established that the sun would always be at one of these two focal points. Okay. Anyway, so your sun would be at a focal point over here, and he said that this area along this arc would be an equal in size of area as any other place along the same within the same time period. So this time, delta 1, T1, and delta T2 would be the exact same amount of time, and this area would be equal one another. Now, what this really points to, now that's an interesting phenomenon, but really what's the interesting part is it shows that the speed of your orbiting body actually increases as it gets closer to the focal point that has your mass, your center mass. So as objects get closer to the sun, they're going to increase in their speed, and then they are at their slowest speed when they're farthest away from the sun. And you're probably used to this idea. Science fiction movies and books and things like that, video games all talk about using the slingshot effect. But they can get close to the moon or whatever, and then as they go around the moon, they can go get a slingshot from the mass and then speed up along their way along the other path, so on and so forth. And so that's the entire idea, is that the equal areas are swept out in equal time periods. And then we get to Kepler's third law. Okay, and this one's a little bit more it's a little different. Okay, so the first thing that it does is it relates the orbital period, and that's represented by a capital T, okay, to the distance from the sun. Okay, now the period, just like in a wave, remember a period in a wave is the time it takes to go from like peak to peak, right? And so like it's the same idea. It's the time it takes for one revolution. For the period of the Earth is 1 year, right? Because that's how long it takes for us to go around the Earth, around the sun one time, or 365.25 days. Okay, but anyway, so that's your period, and so it's the time required. And so essentially what it says is that as your radius increases, your period increases, which makes complete sense. The farther away you are from the sun, the longer it should take you to go around the sun. So that's essentially what it says. Now, the idea is, what makes it interesting is that he came up with these two values, that they're related by the cube of the r and the square of the period. So they're not directly proportional, but they go in the same direction. So as your r increases, the cube of that is equal to the square of the t. Okay, and so anyway, and then it's going to have the same value for any object orbiting the sun. Okay, and so what you find out is that you can do a little bit of math here. You can find out that t squared is equal to some constant that's, let me see if I can remember, 4 pi squared over g times m times r cubed, right? And so you get this guy here. Pretty sure that's what it is. Anyway, but you get a constant here, and then you get this proportionality, and we proved that in class in our little activity. Okay, there's a couple of equations for planetary motion you need to know. Okay, so this relates period with radius and mass. Remember, g is the universal gravitational constant, 6.626 times 10 to the negative 11th, and v sub t is your orbital speed, also your translational, no, not your tangential velocity. Okay, and that relates your mass and your radius. In both these cases, this would be the mass of the central object. So if we're talking about things orbiting the sun, it would be the mass of the sun. If we're talking about things that are around the Earth, then it would be the mass of the Earth. Now notice this part here, it's for a circular orbit. So we can only use these formulas when we're talking about something that's in a circular or very nearly circular orbit. As soon as it becomes more and more elliptical, then we have to worry about some other factors, and the equations get much more complex. All right, so let's do a couple practice problems here. All right, so you got a large planet orbiting a distant star is discovered. The planet's orbit is nearly circular. Okay, so that means we can use one of our new things here. And close to the star, the orbital distance is 7.5 times 10 to the 10th meters, and its period is 105.5 days. Calculate the mass of the star. So we've got two formulas. We need mass. They both have mass in them, right? You've got mass here and you've got mass here, but we want to use this guy for this equation because it gives us period. All right, so let's write down this formula right here. Oop. So t is equal to 2 pi times the square root of, and I wrote it down, r cubed over gm. All right. So we need to, and it says calculate the mass. So that means we're going to have to do a little bit of finagling here to get our, to solve for mass here. Okay, so I'm going to take this equation and we're going to solve for mass. So we're going to do a little bit of algebra. So let's divide by 2 pi on both sides. So we get, so let's see, So t over 2 pi is equal to the square root of r cubed over gm. Okay, so there's that guy, square root of r cubed over gm. All right, now we're going to square both sides to get rid of the square root, and so we get, let's see, we're going to do it left to right. here. So t squared over 4 pi squared is equal to r cubed over gm. Okay, and now we're gonna, let's multiply both sides by gm because we want that on its own side here. So gm times t squared over 4 pi squared is equal to r cubed. Okay, and now we need to get the m by itself. So that means we're just going to multiply by the things that are in the bottom, divide by the things that are at the top. So we get mass is equal to, let's see, so it would be 4 pi squared r cubed over gt squared. All right, and then now we have it solved for mass. Okay, and we can plug things in except for our period. Now remember, in physics we never use days for our SI unit of time. We have to use seconds. So we have to convert our 105.5 days into seconds. So we got to do a little bit of dimensional analysis here. So for every 1 day, we have 24 hours. Okay, and then for every 1 hour, we have 3,600 seconds. 1 hour, we have 3,600 seconds. So let's see. So 105.5 times 24 times 3,600. So we get 9.115 times 10 to the 1, 2, 3, 4, 5, 6 seconds. All right. Then we can just take all these guys and we can plug them in for our mass value. So R value would be here. Okay. And the t value would be here, the 9.115 times 10 to the 6th. Plug that in, and you should get this as your answer. All right, 3.00 times 10 to the 30th kilograms. All right, let's do one more. It says, what is the velocity of this planet as it orbits the sun? All right, this one's or it orbits the star. So we're going to use our other equation here, and this one's really nice because we're solving for velocity. All right, and our equation is already solved for velocity, so that makes life a lot easier. So g times m over r. Okay, so our g value here would be 6.673 times 10 to the minus 11th. The mass is what we just solved for, so that's the 3.00 times 10 to the 30th. And the r value would be the 7.50 times 10 to the 10th. And you should plug that all in, and you should get this answer right here. I really highly recommend practicing putting these into your calculators because it can, with all these exponents and the square roots and these fractions, or the decimals and negative and positive square roots, or negative and positive exponents, stuff can make life a little bit more complicated. So go ahead and just pause the video, take time to practice punching those in until you can do them reliably. All right, a couple more things here. All right, weight versus weightlessness. We've talked about weight a couple of units ago, and we know that weight is really just a measure of the force of gravity. So weight equals mass times gravity, right? Whatever your mass is times gravity, okay? So when you're standing on like a bathroom scale, getting your weight, essentially what the scale is doing is measuring the downward force that you're placing on it, right? If you push down on somebody that's on a scale, then the number that the scale reads goes up because it thinks you're, or it knows you're pushing down harder on it, right? Whether or not it's the actual weight of the person doesn't really matter. Or if you lift up on the person that's standing on it, then their mass or their weight will go down because you're putting less force. So really you can think about it that the bathroom scale is essentially just measuring the normal force that it is applying to you. Okay, so if you think about it that way, remember the normal force is the force that's always perpendicular to the level surface that you're standing on. So the person standing on the balance pushes down, and the normal force is what's pushing it back up. All right, so that's really when we think about us feeling weight. Whoops. When we're thinking about us feeling weight, essentially that's what we're feeling, is this idea of, well, or like we're feeling the force of the earth pushing against us, or the force of the chair I'm sitting on, or whatever. Or if you're standing up or sitting down, laying down while you're watching this, then you're really just feeling the force of that thing pushing back on you, and that would be the normal force. So if you remove the normal force, then you'd feel weightless. Like if you've ever been on a theme park ride, like at Disney World or Worlds of Fun or Six Flags or anything like that, one of the ones where they shoot you up in the air and then they like kind of drop you and you kind of feel like you're floating there, right? You feel like you're weightless. So it's called apparent weightlessness. All right, and it happens when you are falling at the same rate as your surroundings. So really, because there's nothing supporting you, you have zero net force at that time. Okay, and so really that's what gives you that feeling of weightlessness. So when astronauts are in orbit, they're not weightless. They have weight. The force of gravity is pulling on them. We can calculate the force of gravity, right? We have the universal law of gravitation. So we can calculate that. So we know they have some force of gravity acting on them. So therefore they have some weight. However, remember when you're orbiting something, essentially what you're doing is you're just falling and missing over and over again, right? Your object, you're going around and you just kind of like you've got enough vertical velocity that you go around your object and you just keep missing it as you go around. And so really you're just just falling over and over and over and over again. And so when you're in a capsule that's doing that, the capsule is also doing that, right? Going around and around and around. And because you and the capsule, or the astronaut in the capsule, have the same falling rate, okay, they have no normal force in relation to each other, and so therefore that's why astronauts are weightless, or so they have this apparent weightlessness. Okay, so true weightlessness really can only occur if you're very, 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 very far from any other masses. Okay, so very far away. This is practically impossible because remember our formula for universal law of gravitation is constant times the two masses divided by r squared. And so no matter how far away you are, there's still going to be some masses that are acting on you unless you find yourself in an alternate dimension where you are the only thing that's in there. So anyway, so do your practice problems. This is pretty, just memorize those laws of, or Kepler's laws of, Kepler's laws anyway, and do your practice problems. Let me know if you have any questions. I'll see you on the flip side.